So good morning all of you. Today we are going to see the third session in analog and digital communication module 1, amplitude modulation. In the previous class, towards the end of the class I gave you a problem. I wanted to see how many of you have solved it. This is the question for the problem. How many of you have solved this problem? The output signal is given to you and you are asked to find out the value of modulation index. Very easy, very simple problem. So this S of t is given to you. S of t means the output signal after amplitude modulation. 5 cos 1600 pi t plus 20 cos 1800 pi t plus 5 cos 2000 pi t. This is the output signal after amplitude modulation. You are asked to find out to what extent it is being modulated or what is the value of modulation index. How many of you have done it? Very good. What is the answer then? 0.5. So the S of t is given as 5 cos 1600 pi t. So from which we have to rearrange this equation. Vc is equal to sine omega ct plus mvc by 2 cos omega c minus omega m minus mvc by 2 cos omega c plus omega m. From this we'll compare this, you will get as Vc to be 20. So from this what we'll get the value of Vc to be 20, right? Omega ct 2 pi fct. This is 1800. The other one, see this one. Sorry. Yes, 1800. From this we'll get the value of fc. Similarly, we'll get the value of fm. Right? Yes or no? Are you all able to understand? So, the value of m is 0.5. Another one more problem. Consider a sinusoidal modulation in an AM system. Assuming no overmodulation, the modulation index when the maximum and minimum values of the envelope are respectively 3 and 1 is. In this problem, Vmax is given as 3 volts and Vmin is given as 1 volt. You are asked to find out modulation index. I am trying to cover up as much as possible all kinds of problems so that you can perform well in the exams. You will be able to do any kind of problems that comes in the exams, and it is always better to attempt problems because there are more chances that you will get full marks out of it. Is that clear? So if you have any doubts regarding any problems, anything that you want to discuss, you can give it to me. That also can be discussed. So how are we going to solve this? Very easy, no? Vmax is given, Vmin is given, modulation index Vmax minus Vmin by Vmax plus Vmin. So modulation index is 0.5. 3 minus 1 by 3 plus 1. It means that we have modulated the signal to a 50% level. Sometimes you may get questions based upon the percentage modulation also. If you get m to be 0.5, it means that percentage modulation is 50%, right? Okay. Now let us see what are the different types of modulation. There are different types of modulation, different ways of amplitude modulating a carrier signal, each of which results in different spectral characteristics of the transmitted signal. Basically, what we are doing is that we are generating a carrier signal and we are modulating it. Amplitude is changed according to the message signal, according to another signal that is being automatically created. Like say, for example, when I am speaking to in previous a few in 90s and 80s and all, you could have found that there are AM radios also. Today we have only FM radios, right? Due to so much of advantages when compared to AM, only FM is used nowadays. But when we had previously, we were using amplitude modulation for broadcasting or radio systems and so many other several applications. Wherever we require communication systems, we were using amplitude modulated waves also. So in that case, we had different types of modulation. The objective is that you are changing the carrier signal's amplitude with respect to the change in the message signal's amplitude. This particular amplitude modulation can be done in multiple ways. So many ways are there. What are the different ways is what we are going to see in the coming slides. First one is the conventional double sideband full carrier amplitude modulation. The second one is double-sided suppressed carrier amplitude modulation. The third one is the single sideband amplitude modulation. Fourth one is the vestigial sideband amplitude modulation. In this, we will be covering in depth the first three: conventional double-sided full carrier amplitude modulation, which we have already seen. The ordinary way of amplitude modulation, we call it as double-sided. We have two sidebands, frequency for the upper sideband and the lower sideband, FC plus FM and FC minus FM. Double sideband suppressed carrier AM. In conventional double-sided full carrier FM, you have three frequency components: FC, FC plus FM, and FC minus FM. In double-sided suppressed carrier amplitude modulation, you don't have the FC component at all. You only have FC plus FM and FC minus FM. Single sideband, you have only one sideband. Okay, vestigial sideband, you have a different method that we will not be seeing in our, because it is not there in our syllabus. If you want, I can conduct a special class for that. Those who are interested, we can do that. Otherwise, it is not there. We are not going to see in depth. So the first one is the ordinary one. Previously what we have seen is that you have three frequency components. All the three are transmitted. But what we have to study is about the suppressed carrier or a signal in such a way that you don't have the central component, but you have only FC plus FM and FC minus, let us call this as FC minus FM. This is FC plus FM. So you don't have this component. So you have suppressed your carrier. This type of amplitude modulation is called as double sideband suppressed carrier modulation. The transmitted wave consists only of the upper and the lower sidebands. The transmitted power is saved here through suppression of the carrier wave, but the channel bandwidth requirement is same as before. We do not have any kind of advantages with respect to bandwidth because we have to transmit both these upper and sideband, upper and lower frequency bands, sidebands. Okay, so double sideband suppressed carrier, as the name tells itself, the carrier wave or the carrier frequency component is suppressed and you are transmitting only the upper and the lower sidebands. This type of amplitude modulation is called as double sideband suppressed carrier or DSB SC modulation. Single sideband modulation, in which the modulated wave consists only of either upper or the lower sidebands. What are SSB? Amplitude modulated systems. This is only an introduction. As we go on, we'll study in detail. It requires minimum transmitted power because you are transmitting only one sideband, either upper or lower. In the previous one, double sideband, you were transmitting both the upper and the lower sidebands. In this, only one sideband, single sideband, only one frequency component is transmitted, thereby saving both power as well as bandwidth. In the previous case, so what is the difference between double sideband and single sideband? What is the advantage of single sideband? You can reduce or you can save the bandwidth also in single sideband, but in double sideband there is no difference in bandwidth. Okay. This is the advantage. Now, disadvantage is increased complexity and limited applicability. Single sideband modulation is particularly suited for transmission of voice signals. There might be questions. See, previous somewhere in the gate question paper, I've seen that this question was asked, what is that? Which of these following amplitude modulated waves are more efficient in bandwidth? One DSB SC, double sideband, single sideband, and so and so and so. So the answer would be single sideband. Okay. Which is more bandwidth efficient? Vestigial sideband modulation, in which the sideband is passed almost completely and just a trace or a vestige of the other sideband is retained. The required channel bandwidth is therefore slightly in excess of the message bandwidth by an amount equal to the width of the vestigial sideband. This form of modulation is commonly used in television channels, not these days but previously. Okay, vestigial sideband. This question, vestigial, we will not be seeing in detail, but in general, if there is a question on what are the different types of amplitude modulation, you may need to give a small briefing about one or two sentences about vestigial modulation. So for that, I've introduced that here. The other three we will be seeing in detail. So this is a general block diagram. You have an oscillator that generates a carrier signal. You have an audio amplifier. You pass it through an RF amplifier and then through a class C modulator, and then you transmit an signal. Here is where you get the output of the amplitude modulated signal. The oscillator is used for generating carrier signals, which is then amplified. Only the radio frequency components are amplified, so we call it as RF amplifier. So you get an amplified signal here. Similarly, the speech signal is also amplified. The audio signal is also amplified. Amplitude modulation in previous generation were primarily used for broadcasting only voice signals. This is the foundation for today's wireless communication, 5G, 6G, and all those things being in existence today. All these things started from the basic amplitude modulation. So you have to be very much thorough with what has happened before if you need to study what is going on today. So let us see in detail what is double sideband suppressed carrier amplitude modulation. What is the advantage? Why should we suppress the carrier signal? We'll see this in detail. A double sideband suppressed carrier amplitude modulated wave is obtained by multiplying the message signal with the carrier signal. I told you have two signals, message signal and the carrier signal. We are multiplying message signal with the carrier signal so that we get the double sideband suppressed carrier amplitude modulated signal. Let the message signal be denoted as M of t, and it is impressed upon the amplitude of the carrier signal called as C of t. Conventions and the nomenclatures may vary as we go on. That doesn't matter. Wherever you find it confusing or wherever you find it difficult to understand the concept, you can ask me. I will repeat these concepts again and again till you understand. There were instances where I had to repeat it 5 to 10 times in certain classes. I don't bother that. I want all of you to be very strong in your basic concepts in such a way that you can present yourselves in your examinations. So what is double sideband suppressed carrier? You are suppressing the carrier and you are sending only the sideband signals, both the upper and the lower. Whenever it is double, it means that you have both the upper and the lower. When it is single, it means that you have either the upper or the lower. Very easy to remember. The name tells you everything. So let us consider, we have already given that the carrier signal C of t is equal to AC. Let us consider the carrier signal AC, C of t to be AC cos 2 pi fct plus 5c. So basically, any electronic signal or any electromagnetic radiation consists of three important components. One is the amplitude component, the frequency component, and the phase component. Okay. So we take the signal to be C of t, the message signal to be M of t, and the output of the carrier signal, that is DSB SC signal, to be U of t. We are multiplying MT into C of t. So C of t is an oscillator generated ordinary carrier wave. Is an ordinary wave which we can generate according to our convenience. The carrier signal is generated according to how we can define. But the message signal is not done like that. Message signal is undeterminable. It's something, it is unpredictable. Okay, you can't determine what would be the message signal. Sometimes I'll be speaking continuously, sometimes I'll stop for all of a sudden for a long time. When I stop, there is no message signal and only the carrier signal is being transmitted. Sometimes I may speak very loud. That means that frequency or the signal has a higher amplitude, it usually has a higher amplitude. Okay, so the message signal is something that is unpredictable and keeps changing every moment. But the carrier signal is an oscillator generated signal which is going to change according to the message signal. Is that clear, all of you? So let us do. So far we have not seen any Fourier transforms or Fourier series coming up into our question. Now what we are going to do is that we are going to convert these time domain signals into frequency domain signals. In that the signals are the same, we are going to analyze things in the frequency domain. So how do you convert a time domain signal into a frequency domain signal? You take the Fourier transform of the signal, right? So we have understood that u of t is equal to m of t into c of t, right? You are taking the Fourier transform, this m of t becomes Fourier transform of m of t, this multiplication is convolution, and this is the carrier signal which we have generated with the help of an oscillator. When we take the Fourier transform of m of t, what happens is that all the time variables are converted into frequency variables, right? So that now m of t becomes m of f. And when we take for the carrier signal, what happens? We get AC, this is a constant. Here, since you have this, you have here AC by 2 e raised to j phi delta f minus fc plus e raised to j phi delta f minus fc. What is a delta signal? What is an impulse signal? You might have studied in your signals and system what are the basic signals that is available? What is that? You remember? If you don't remember, please go through your previous subjects and just come back to me. If you have doubts, I'll clear it up. Okay. So in this, what happens now? You see that in Fourier, in frequency domain, you have two components: Fc plus F plus Fc and F minus Fc. This F is nothing but Fm. That is the message signal frequency. So the output waveform or the spectrum of a double sideband carrier modulated signal, amplitude modulated signal, will be like this. And you can see that the message signal has been shifted in the frequency domain by a factor of Fc, where Fc stands for the carrier frequency. So the frequency content of the modulated signal in the frequency band where modulus of f is less than fc is called the upper sideband UOF, and the frequency where f is greater than fc is called as the lower sideband UOF. So what is the upper sideband and the lower sideband? The other characteristics. See, this equation is very important, so that you need to by heart this equation or you need to use it in several places. I'll tell you why it is the other characteristics. That's why I have repeated the equation in almost every slide. You don't need to write it again, but you need to remember it. The other important characteristics are the speciality of this is that you don't have any carrier component while transmitting. That is why it is called as suppressed carrier. So the name double sideband suppressed carrier itself tells you that it has both the sidebands, the upper sideband and the lower sideband, but does not have the carrier signal along with it.